Hello. Oh, test. Test my microphone. I can never know. I hope my microphone is connected. I'll get better at this. Anyways, welcome back to another low quality stream. I have not resolved my stream quality issue just yet, but I can't stay off my content creation schedule lest I start missing days. I don't know. I'm trying to just stay consistent and resolve the issue when I can. So one of the potential solutions is to go downstairs in my living room and I'll stream from close to the router. And in fact, I might be able to run an Ethernet cable if I'm at that distance. The trade-offs are, of course, that I won't have my dual monitor set up downstairs. I'd have to move it so that I could do these sorts of streams because, well, I need to be able to see both my programming environment and I'd like to show the book while I'm talking through the material. Like I thought about maybe I'll do it for my laptop and then I'll just use my book and like talk through some of this stuff. But I think one of the features of this being a learn with me is that I get to also share the content with everyone else. So if they wanted to follow along or interact in chat and talk about the content while I talked about it, it sort of facilitates that. Not that, from what I looked at the stream quality, it's not that anyone would be able to even really get a solid view of the website from the video quality, but nonetheless, this is sort of what we're working with for right now, and I really want to keep going. Okay, so last time we started the chapter 3 on vectors, and we looked at some of the main types, data types of vectors. And we talked about some of the characteristics of these data types. Specifically, we went into the atomic. Every time I look at atomic, the word, I think atonomic, or like much more complicated word than what it is, and then I like sort of get tongue-tied about what I'm about to say. So atomic is what we looked at, and we looked at all of these data structures that are fit under the atomic data type, and we discussed how these structures interact with one another when we're creating vectors specifically, and how, as we're identifying if a given object in R is one of these types, or how when we bind objects to values, how they might get coerced to one type or another, particularly when they are in this sort of combined framework, the C, because of vector coercion here, and how coercion might impact code down the line. And then we just talked about tests for identifying if something was something else. And you could also do these sort of deliberate coercions of variables, and how when you do a deliberate coercion, how might this then change the characteristics of the data type. So next we're going to move into attributes. Attributes is really cool. I'm hoping to get through, realistically, I'll try to get up to lists tonight. I only want to be on for like an hour or so. But, if the pace is right, we might make it to the end of the chapter and then I can start subsetting. Which, to be honest, I really like the structure of how I'm doing things now. I'm reading the chapters beforehand and then I'm reviewing material on chapters that I read prior. So, for example, I read chapter 4 yesterday night instead of streaming, and now tonight I'm streaming on chapter 3. So it gets like this sort of recall system is embedded into how I'm reviewing the material. So tomorrow, right, I'll read chapter 5 and then I'll stream about chapter 4. And I'll probably read faster than stream or review streams because I do these sort of side conversations. So hopefully I'll still be able to read all the content, and we'll see if we get to cover all the content in stream. And if we get later in the chapters and if someone reaches out and is interested in a particular set of the material they'd like me to cover for whatever reason, then I'll gladly move to that material. While the structure of the book is sort of laid out to get more difficult as we moved into later chapters, it is also have this sort of modular structure for that. If you were interested in particular aspects of the R programming language, you could just go and read about those things. I will say that the foundational or introductory first 8 chapters are something that I definitely am going to try to cover on the stream. So maybe not moving into any chapters before we cover those chapters at least. Cool. Alright, so we're going to talk about attributes. So attributes are interesting in that they're this sort of metadata that's always attached to our code. So we saw a little bit of this in the chapter 3 code when I called it up here. So let's start a new block over here. Start a new block, and as you saw over here before, let's load the tidyverse. We saw over here before was that when I called a data frame, it had a specific set of attributes attached to it, but we've only talked about simpler structures. So let me just do this, and then this is going to get coerced, right? Well, no, because we have these 1 to 5, 1 to 5, same, and they're going to have names to them. So a named vector is a different thing, but only different to the degree that it has additional attributes. So in this case, this is kind of interesting. I think if I do struct, I actually get all this stuff. So maybe class, right? There's a certain structure I'm looking for. Yeah, no, attributes is correct. It was just that it had so little attributes because of it was a vector. But this kind of demonstrates what we're going to see here in a second with attributes attached to specific data types. So in this case, X is bound to a data type of a data frame, which we'll talk about later, is not an atomic vector per se, it's a list, but it still has some of these principal data types that we're going to focus on here. In this case, it has names, and then it has this class and row name structure. Now, names specifically is one of those data structures that is sort of the bread and butter. Everything's going to have this names attribute, whether it's empty or not. Maybe I can get fancy here. I don't know if I can make a name list. Something like that. another sort of thing we can look at here. Maybe if I can do x equals 2. No, I can't do that. But here, matrix, for example, and this is an atomic vector, so this is a little more in line, has the dimension. So I was just trying to illustrate a dimension. So we have a 5 by 1 matrix, right? It's a vector, but 5 by 1 matrix. In R's terms, a matrix is just a vector, but it has these particular characteristics with it. In this case, the matrix is something that has more dimensions, right? So it has additional sort of dimensions outlined. Like if I just wrote, for example, C here, and looked at the attributes, we get null, right? So notice what makes the matrix something different is the sort of the metadata carried with the data type. And you see that as the complexity of the data type sort of increases. I'm not sure if this is true in principle, but at least for when you're looking at data frames, you can see that there's more sort of things specified in the metadata than something like a matrix. So you can add things, and this is going to give you sort of behaviors for the data structure, and that's sort of that's what we'll talk about here. So in this case, we'll talk about how do we get attributes in the first place. Well, we're just going to see you can actually get it from atch. So attribute gives us the list of attributes. So if I did this, then I'd get a nicer structure. Nice. Cool. So this gives me null. Like this. Now we get a dimension 1 and 2, 5, 1. Okay. So the dimension integer is an integer. So this is talking about the characteristics of the attribute in itself, right? Which we know is an integer now. Cool. Okay. Attributes are ephemeral, so most attributes are lost when you do operations. So when you manipulate some operation on a name reference pair or some name, then you lose the attributes. So this is something to be cautious of when you're doing operations on things and you want the attributes to carry forward. It isn't the case that they're always shared, unless there's like have to be special attributes. And here is the special attributes, as like what I was trying to point out earlier. Here, the names and dimensions in particular are these attributes that tend to be preserved and are used to make this specific class of data types known as S3, which we'll talk a lot more about in later chapters, and we'll briefly touch on S3 atomic vectors in the next section. Cool. So now let's break down and talk about the two routinely preserved attributes. So we have names. Here you can create a named vector as such, where the names of each of the elements within this concatenated set of values are assigned using the following procedure, where A is equal to 1, B is equal to 2, C is equal to 3, and now these values are the names that correspond to each of the elements, right? So in this case, I can copy this code, you can look at this, and now you'll notice here that when I looked at the structure of the attributes, oh look, I have a names attribute, and it's going to give me the 3 names that correspond to, well, the values referenced or bound to the name. But you can also assign names in a different way. So instead of doing it like that, You could also assign names by, say, I just arbitrarily assign 1, 2, 3 and bind it to the x. Well, then I could call names. So this is equivalent. And then I'll get the same sort of here. Boom. So you can assign names to stuff. So that's cool. Because names are one of these attributes that get preserved, assigning names might be useful early on. Or changing names. So you can also do this inline. So you can just set names to the values. So set names then can take a function as such, or it can take some input values here and then give them the following names. So here's what sort of is happening. Values name. Technically, when I'm drawing named vector x, I should do it like so. And you can also unname things, which is cool. But instead of doing, so this is just differentiating between how Hadley is going to talk about the diagrams that he uses in order to identify data structures with names. So instead of doing it like this is sort of cumbersome, and since all data structures, or most data structures, are going to have names attached to them, this isn't going to be as practical visually as doing something like this. So just recall when you do this, and we have these little grays, we're doing this. Cool, easy enough. Set names is kind of cool. Okay. Set names is something that comes up again in the questions, I think. And I was just trying to get a little intuition about what set names was doing here. So it's accomplishing both these things. Once again, equivalent, but just does so very elegantly, if you will. And if you think about, if you know tidy, if you know how to use the pipe operator, this is kind of nice because you could take a data set and then you could set names and just put all the names on the set name and then like keep moving through your pipes. It's like tag and keep going kind of thing. So that there's utility in that respect. Something like let x be assigned to 1, 1 to 3. Oh, where'd my code go? Okay. Oh no, I cannot remember how to do this. My keyboard shortcuts. There we go. And then you can set names. And then I'll just take this from here. Set names. And then let's strip the attributes. Should work. 0 arguments passed to attributes. Let me do this. And then we call. Well, that works, but let me clear out here. And then let me call this. Alright, so this is another form then. So you could do assign this to this and then do this. This is kind of like verging on tidy, or you get the sense of how you could do, you get like a tidy workflow out of this. I mean, it could also, if you had done this prior, like this prior, then you could do some like setups here, like rather than mumble my way through this. If X was already set up, then you can do something like this, right? And we give the names to the values. Yeah, it's interesting. Yeah? But notice how when I do this, it doesn't save it. So you have to do like X is equal to X, and then you get them to save. So it's just another sort of way to execute the same equivalent syntax, but it's just nice to think about how to keep like tidy or pipe operator sort of workflows in mind while working with some of these functions. Specifically the ones that have implications for data analysis, which, well, as we'll see, a lot of them. Okay, next particularly pervasive attribute is going to be dimensions. And dimensions is going to be something important when we're talking about, well, arrays and matrices, like what we saw in that quick and dirty example I gave in my dirty code. Also, something about this code, I'm going to be sharing and posting this online. I note that it probably isn't going to be any use or value to anyone unless they're watching the videos and sort of trying to follow along and see some of the particular pieces of code. But everything programmatically in here, unless there was a very cumbersome exercise, is going to be implementable within the GitHub book. So I would just urge people to look at the GitHub book, but I'll post this on my GitHub for prosperity's sake. So whatever you like. Okay, so dimensions here, they're not programming tools, interestingly, that makes that sort of distinction, but we definitely use these in statistics. Matrices, or the manipulation of matrices, is a lot of what we do across many uses of linear modeling, to give an example of something. So that's linear statistical modeling. Notice, not like some sort of fancy model. So in this case, it's just describing what you get out from using syntax to create a matrix. So this is what I couldn't remember before when I was trying to make 2 rows off the 5. So if I turn this into a 6 and then made this second one into a 2, then this is going to give me the structure I was looking for. Yeah, so here we got one of these. We'll get a 2 by 3. And we can observe what those are. I should probably use different things, but different names. I've just been copy pasting this X around, sort of meandering the space, but it's been nice. Okay, so 2 by 3, right? And you can see the output here also, if you wanted to look at. Right, and this is, so that's metadata, right? So that's metadata attached to the name value pair, or just attached to the reference object itself, that states how to organize this vector. Under the hood, it's still a vector. I think that's what's coming up, which is actually interesting to think about. So one vector argument to describe all dimensions. And we can also take a particular name value. You can take an object, a name, and modify the object's dimensions by changing some of the metadata, right? So in this case, we're saying, hey, look at the object here, Z. We're going to go in and change the metadata so that we have a different structure. So many of the functions that work with vectors generalize to matrices, and this is because vectors are matrices under the hood, right? If you think about how R is going to do computation on these things, you'll see that, well, you'll get to see that really it's still going, or at least when it's doing element-wise computation and not specifically matrix. Well, certain types of matrix computation have rules, mathematical rules, but R is going to treat, programmatically R is going to treat a matrix like a vector in some cases, and I think we'll be able to see that soon. Vectors, so right. So this table here is just to show the versions of functions that work to describe things that you might commonly be interested in when you're using vectors, for example. So in this case, like for example, we use this combine function a lot, you'll see, but you can also do this with arrays or a-bind, or sorry, you can also do this with matrices and arrays by using functions like r-bind, c-bind, so row-bind, column-bind, or a-bind to combine to some certain array configuration that you specify in the arguments. So yeah, this many of the just it generalizes. So a vector with a dim is often set to one dimension but has null. We saw this null earlier when I was looking at the dimensions for like this, for example. Right, because then if I took the struct of this, we got nothing. We'll say we get null. Right. Maybe I'll try to get some documentation. Why? It's a characteristic here. It says in the chapter. It's one-dimensional, but has null. So yeah, you can get one-by-one matrices or one-by-one arrays, which is kind of interesting. I guess I'm not sure what the pros of doing that are, really. Unless you were trying to use these particular functions, or trying to generalize use of these functions in a pipeline in such a way that you didn't have to use these. Like, I imagine you couldn't use names. Well, I guess you could use names on a matrix, right? I don't see why you couldn't use names on a matrix. X names X. It's null. Yeah, but we didn't give names to anything in the matrix. But what if I put length here? Length is just going to give me the row as length. Yeah, so here, right, we get length of the vector, which is interesting, right? Because here we have 6. But when I ask for length, I'm asking a question about the length, the vector. For example, if I ask something like row num, or r num, or n row, right? It's going to give me the number of rows, which you notice is 2. So it has this knowledge in it about other dimensions of the object. Do you see? But depending on the question I ask it, it might give me different things. So if I had something that was 1, and I wanted to ask about the number of rows, right, I'd get 1. But if I wanted to retain that this object was a matrix, I might do so because later down the road the matrix might expand in size, but I don't want it to change data structure. Or at least that's sort of one example I could make up or come to mind. Okay, so we have a couple questions here. So let's just run through these questions. Okay, so set names is implemented. How is set names implemented? Oh, well, we talked about set names, but we can take a look at the documentation. Set names, convenience function that sets names to an object. It's useful at the end of function definitions where one is created, the object. So it takes an object and then some names. Unname is for removing names, and Mr. Bates. Mr. Bates, you'll see, maybe not in this book, but he's quite the guy in terms of his contributions. I'm sure name I would butcher if I said out loud is also has many contributions, but you know, Bates. Okay. Right, so the examples it gives, but it didn't ask me about examples, right? It asked me about implementation. So we can also, remember if you press if you're on a Mac, if you press Command and then click on a given function, then you can take a peek inside. In many cases, it's just going to give you a read-only version of this. In fact, I think in every case when you do this sort of peek in, it'll give you a read-only version. But let's see, the read-only version is going to give us, and this is useful, and I encourage everyone to, if you have some functions that you use frequently, go inside and take a look at what's under the hood and what makes them tick. You might learn something about the particular procedure that is used that you could then go and modify and create a more useful version of that function for your own needs. So custom function to come out of exploration of. And you also just get to see good code, right? This is code really written by smart people. I mean, this case is kind of very trivial, but it's written nicely. So in this case, this is a convenience function, right? So set names is just going to call names, but it's going to call names a bunch of times. The name of the object is going to be the name of these. So it's just calling names, and then it's outputting the object. So it's letting you do this sort of assignment process all in one function. Normally, as we saw, you would have to do this by like laying out the names and then calling them the names here of X. And then you'd also have to have this sort of object. You'd have to have this object bound or referring to some set of values already. Or some values. And so this simplifies this two-line process into a single-line process. Very cool. We can also go look at unname. So unname here. Unname removes the names or it removes dimensions too. Dimensions can have names. Force. What's force do again? Force is either something that one issue we might see coming up is that when I review material in later chapters, I might think about or learn about terms that we haven't seen yet. So I have to make sure that I don't talk about things in a way that makes the assumption that it was already something that we discussed here. Either way, come here. Okay. Wow, feed up streaming. Nice. Okay. Either way, I don't recall what force does, but I think it came up in chapter 4, and that's why it's coming to mind. I'm not going to check that. Yeah, but I'm certain that we hadn't, or more certain that we had not yet reviewed force. Cool. But here, let's talk about the implementation of unname then. So what's unname doing? It's saying if that we have a name, so it's taking in an object and it's doing this, it's taking in the second argument forced. So what it's first is checking if the is null is not true for names of objects, then, because we have this exclamation point, we're talking about in that way, then turn names, objects, into null. So if there are names currently, we're going to make those names null. Then if names, dim, and we have force, so if force is not equal to is data frame object, then the dimensions are null. So I was trying to avoid talking about force, but force is coming up too much. I think force changes dimensions of the structure. So by forcing or doing this sort of coercion, we change something about the structure of the data structure. Or normally when you do this, you might change something about the data structure, but you want to prevent doing that sort of change when you are doing this process. Specifically, I think if you're stripping dimensions from an object, like it seems like that's something that, by taking a dimension from the object, you might also lose that dimension, maybe? And this is preventing the reduction of dimensionality from occurring in the data structure. So what are you saying is don't take the dimensions from me, but just make some of the dimensions nameless and others have names. Makes sense? Maybe not. That might be cap, but that's sort of my intuition on what I remember about forced specifically, but we looked at unnamed. Okay, what's dim? Dim looks at the dimensions. When applied to one vector, it's 1, or it's null. When might you use n row, n call? When you're working with matrices or arrays, for example, or something. Okay, easy enough. We don't have to explore that too much. What would you describe the following 3 objects? What makes them different from 1 to 5? Okay, so in this case, we have a 1 by 1 by 5. Cool. So 1 row, 1 column, 5 times. And in this case, we have 1 row, 5 columns, 1 time. So a bunch of rows of 5. So 1, 2, 3, 4, 5. This is 1, 2, 3, 4, 5. This is 1, 2, 3, 4, 5, and then this is down 1, 2, 3, 4, 5. We can take a look at each of these. Alright, let's spit them out. See? So this is going to give me each one 1, 2, 3, 4, 5. And then the second one is going to give me this columns, 1, 2, 3, 4, 5. And the last one will give me the rows. 1, 2, 3, 4, 5. Cool. So note then that an array, the first one is going to be what the values of the object, or it's going to take in that object. And then the second argument is going to splice the values into some corresponding configuration of a multi-dimensional values. I mean, the values are still like all the same, but it's just going to alter the configuration at multiple dimensions, and this can be any number, I believe. You can go up to a lot. Maybe do something like this too. And call this. It's kind of crazy then. Yeah, 4 dimensions hurts. I've seen 3-dimensional arrays. 4-dimensional arrays seems like it starts to get wazoo, but really it's an organizational structure. And I guess the only application that I've seen, and I don't think no, you might be able to catch some of this in my YouTube series about Bayesian cognitive modeling, but one application is for storing parameter estimates from traces when you're doing Bayesian inference. So when you're doing this process called MCMC, you get like potentially 10,000 simulations, and you want to store these simulations in a sort of convenient way. And one convenient way to do this is to create one of these array structures where each of the sort of contents at one particular level of the dimensions is all the like 10,000 samples. And then you could have another layer, then address that this is all 10,000 are for parameter A. Or from simulation 1, we have these parameter estimates, and then for simulation 2, we have these parameters. Anyway, so it can help for convenient storing of complex structures. But that's sort of a arbitrary, not relevant, probably confusing example that I wanted to say out loud. That's my streamer. Say it out loud. Cool. So copy and illustrate structure. Okay. What is structure? My attribute. What does you want to know about it? When you print that object, you don't see my comment. Why? Is the attribute missing, or is there something else special about it? Structure. Structure returns a given object with further attributes set. So 1 through 5 now has attributes. I wonder if that's kind of neat, use of commenting. Did I just learn this? Huh. No way. Okay, so look. This is not relevant to the lecture, but this isn't a lecture, this is more like a learn. It's a learn with me, but because I'm lecturing to myself. But one sort of thing I just realized in Markdown, you can do this. Yeah, that's so cool. You can do this continuous commenting by using pound greater than sign, and then every time you press return, it will start a new row for the comments. That's very convenient. I'm gonna have to look into that. Ah, look at that. We're already learning weird, fun features about R. So the thing I'm gonna test here is that if I looked at the structure of 1 to 5 now in memory, in this particular environment, does it just have this attribute attached to it? It does not. So what if then I did this? And then did this. It's attached to it. Adding a class will ensure okay. So basically structure, this is going to let us attach attributes to particular values, but it looks like that the ephemeralness, or the sort of, I've said sort of too many times this lecture, and I tend to do that when I'm uncertain about something, so once again, might be cap, or I might not know what I'm talking about here, but the reason why my attribute goes away is that when the object gets pressed through structure, the attribute, since it's not dimensions or names, just disappears. So it might initially get attached, but then because it's not one of these sort of primitive or primary attributes, it just disappears. No idea. we're gonna look at the solutions. Contrary to other attributes, the comment is not printed. Note that some attributes are treated specially and have restrictions on the values that can be set. We can retrieve common attributes by calling them explicitly. Let's look at their example using foo. Foo's are, the name doesn't matter, but I'm just sticking to some of the code just to. Okay, so you can call the attribute. It'll come up here too, right? So come up here, and then the values are the same. Okay, so it looks like you can access the comment attribute. But it might disappear if I did like foo plus one. And then we got new foo. And I still got the comment attached to it. Let's go. Okay. Comment is sticking around. Interesting. Okay. So let's keep it moving. Because we're at about 50 minutes, so it looks like we're gonna get up to lists, just like I said. So here is another important vector attribute, which is class. And classes are specifically important when we're talking about another type of structure under the atomic vectors, which are S3. So these S3 objects are derived from, and these S3 vectors are derived from other atomic data structures, but they have classes, so they have this metadata that gives them unique properties. And this is where factors come out. So in your intuition might think that a factor is a character, right? But actually, a factor is an integer, and it's just has this class, this metadata attached to it, such that it transforms it into what's an S3 object, and now it has these unique properties. But under the hood, do note, or it's of note, that the factor is still an integer. I actually talked to my lab mate about this fun fact I read the other day, and he was definitely took it as unexpected. I mean, it's funny. I mentioned all these like weird, quirky artifacts I'm learning, sort of offhandedly, because I think it's comical to talk about them, because this is really how I want to spend my free time when I'm working all day on my PhD work stuff, or my research, or class work. But I don't know, I really enjoy this material and the opportunity to sort of just digress like I just did right there. And it's nice to just chat along through something that certainly is really interesting to me and has a lot of intrinsic motivation behind it. So not to get all touchy-feely about R, but I like this language a lot, and learning about it is really fun. So let's keep getting into it. Where was I? Right, so we're going to talk a lot more about S3 objects when we get to object-oriented programming later in the book. But right now, what's important is that when these objects, these S3 objects, which become S3 objects when they have particular classes attached to them, are passed into some generic function, they're going to behave differently than they would if they didn't have those. So if people are familiar with sort of introductory data analysis in R, you might learn something about regression, specifically a linear regression, the LM function. We know that the behavior of factors, for example, rather than numeric atomic vectors, are going to behave differently when they're passed into the LM function. So this is a good example of how you get different behaviors outside of some of the functions that you would use in R based on some of the meta attributes attached to those functions, or to those vectors. So we're going to talk about a couple important ones. I'm actually not going to talk about date times or dates. I'm not particularly interested in manipulating dates and times, so I don't want to really go over the material, and I think we can spend our time and get to the end of this section. So, and a lot of material is about these S3 objects, or at least when they're initially going to be introduced, they're going to touch a lot on dates and times and difference in dates and times, and how these S3 objects sort of lend themselves to, I did it again, how these S3 objects lend themselves to working with dates and times data, which is common in some domains. Right now, though, let's just talk about a factor. So factors is this first category, categorical, built on top of integers as we saw before. In this case, we're just taking a list of character vectors, or a vector of character elements, and they're going to have two levels here. So we're taking the factor, we're wrapping it in the factor function, and that's going to output this. But if you looked at the type, we put character, but it's actually integers now, right? And the attributes are going to be these two levels, class. So if we looked at the attributes, we get two levels. So what you get out of using factors is a class and levels. So the class is going to be a factor. You're going to have levels. You can also have values for these specific levels, right? So 1 and 2 in this case. And we know that to be the case because factors are integers, and they're going to come out in this sort of ordinal fashion. Not that the factors in themselves are going to be ranked, but the values starting from the first to the last are going to be enumerated in an orderly manner. Right. So factors are useful. So you want to manage when a factor or character is going to be useful in your data. And this is something that gets pointed out in this section, I think, actually, where he gets into a discussion where a lot of people are transforming character vectors into factors, and they're doing so at the wrong times. And you might save yourself some headache, specifically when there might be some coercion that might happen. If you just kept it as a series of character vectors in many cases. So this is what the diagram looks like when we have these names or these levels referring to these attributes, where we have class and we have levels as the two attributes. So they're really useful when we're trying to get a sense of how much of a given quantity category is observed in the set of values. So in this case, you can see we can use the table function, and we'll get back 3 of m, which is, not that informative because it doesn't give us a sense of all of the possible combinations available in the sex characters. But if you notice, if we did this with the second version and we grabbed factor and we assigned sex characters and we specified that there's actually 2 levels here, so now in the structure we know there's 2 levels. When we call table, we're going to get this information about there being no females here. And that's not something you would get in the former case, right? So we're going to get a richer set of information about the contents of the object, specifically related to the different categories. That's cool. So here, order factors, once again, is something I briefly touched on, but now in the attributes, I actually don't know if it says it in the attributes. Let's see what it says in the attributes. I think if it specifies in the attributes as this is ordered, but we know it's ordered from that, right? But what about in the attributes? Does it tell me? So now, in addition to just getting the class factor, we also get this ordered class attached in the metadata. That's what I would predict. That makes sense. Like, how else would they store the ordering in the summary? Like when you just spit out a little output from calling the name. Okay, so you tend to encounter factors very frequently because many R functions convert vectors to factors. So this is the point that he wants to make here. So you might not want this property to happen. We don't like when coercion happens, right? And it could be the case that this happens without your knowledge of it happening, because it's sort of the base default for some of these functions. And so to eliminate that behavior, we want to set strings as factors to false. And there seems to be this like long-winded, I don't know if it's long-winded, but there was a conversation that happened from Roger Pang, or like a blog post that talks about the history of string is false being defaulted to true. And this other piece by Thomas Loomy. So I know Roger Pang. He's actually I don't know Roger Pang, but he's a biostatistician at Johns Hopkins. And he is the host for 2 of some of my favorite podcasts, The Effort Report and Not So Standard Deviations. I listen to both. It's actually kind of interesting to see his behavior vary as a function of the topical matter. And in the Effort Report, he's much more academic, right? Because it's a conversation between him and a collaborator, and the topics are more academically oriented, right? But Roger Pang and Not So Standard Deviations is with someone who used to work in industry, who was trained as a biostatistician, or trained as a statistician, and worked in data science, and their conversations are a little more wide-ranging and gossipy and sort of more lighthearted. I mean, there's space for the effort report to be lighthearted, but you can definitely feel a difference in sort of, I won't say sort of, you can definitely feel a difference in the conversational type across the two. Anyways, Roger Pang, much to say about data science, so I'd buy something written by him. I might actually go check this out. It seemed to give me an error there, but I'll circle back. I'll try to touch it. I'll leave it up actually. Oh no. Okay. So while factors look and behave like character vectors, they're built on top of integers, so you want to be careful with them. Some string methods automatically coerce factors to strings. Others will throw an error. And still, others will use the underlying integer values. Okay, so keep in mind, right, that we have these different types of atomic vectors. So vectors are going to behave differently based on the data structure type. So it's usually best, and this he gives a recommendation of best practice. So best to explicitly convert factors to character vectors if you need any string-like behavior. So if you know you're going to be using data like strings, keep them as strings and then change them to factors as necessary. Don't front load factor changing. And then you might think you want to do something like this, but I certainly know when I started learning R, at the beginning of my script, I'd import and I turn everything into factors. I didn't use this sort of behavior from the read files per se, but I would go in and I'd set all the levels and names for the factors right at the beginning of the script, and that might bit me in the butt. I think if I had, I don't know if it changed anything about the analyses per se, but it wasn't best practice. Like I could have altered and created factors as needed and retained the raw structure of the data in a form that was amenable to like whatever changes I needed to make moving forward. I didn't need to change everything for no reason because I was changing things. So there's principles there to think about. Okay, so we got the dates. I'm not going to talk about, I'm going to breeze through this material here because I'm really not interested in talking about dates and times. And I want to set it up so we start talking about generic vectors, or otherwise known as lists, when we get back into the material tomorrow. Or not tomorrow, but the next day I stream. Right. And I also know, I think I'm going to have to stream without my mic. I don't know if I'm going to be able to bring my mic to... I'm going to be out of town this weekend. So that might make for some complications in terms of streaming schedule. I won't let you know, but if you don't see me upload, no, there were some complications. Okay. Cool, so dates. Dates are stored with respect to this sort of date, and there's historical reasons why this date was chosen. It's some date important to programming. Date times. So there are useful ways to store date times, and Hadley has built functions to work or with date and times, like lubricate. He also has built like forcats functions, or he's part of the team involved in forcats, which is something to manipulate factors. Then they have functions to manipulate date time. Date times are cool because you can set the structures, and then because in the metadata and the attributes you can change specific things and it will alter the behaviors of the date time information. You can also look at durations, so time since events. You can set the units of these events. So you can see that these are built on top of doubles, right? So diff times is built on top of doubles, and you can look at time since particular things, or difference in time from something. So if we had put in some dates into this function, then you could look at time since particular dates. So that might be useful. Honestly, I don't know. Doesn't come to mind. Like maybe if I was making some automated user interface where I wanted this timestamp, the last time someone was on, or the last time someone was on, I'd write it, and then I could, maybe if I wanted to print some update that said, it's been X amount of time since you've been on, then durations might be a nice, convenient way to extract that information. Okay, great. So we got to 3.5 today. We have 3 questions here. So what sort of object does table return? What is its type? What attributes does it have? How does its dimensionality change? Table outputs. Function will help the base table to fit vectors. Table creation. So it's a method for class table. So it outputs tables. Tables are a specific S3 object. So things that get output from tables, or if I were to, for example, save a table, let me go up here. I'll copy this factor code, and I'll demonstrate what I think I'm talking about. So here I can save this. I can output these tables. I can also save this as T here, right? So here then, and then if I looked at the attributes for T, we would see table. Okay, so it's another sort of S3 object. It's the following dimensions, and then we also get these dimension names. So here we're getting dimension names for if there were more dimension names, like if I named T, which is, say I said table, I don't know if this is the right syntax. This won't work. Maybe I can add structure. Yeah, this might work though. So maybe I can put some structure in. Yeah, so I add some more comments by table. So the object class is table, so that's the S3 object. Tables are going to behave special because they're an S3 object, and S3 objects, when they're passed into generic functions, they're going to behave differently. So if I'm printing a table, it's going to behave differently. And then these other attributes for the table are going to be specified as a function of the data structure. So in this case, right, because we have a factor, we're going to get this dim names factor levels here. Cool. Next, what happens to the factor when you modify its levels? So here we have a factor, which is letters, so it's all the letters. We're going to have 26 or something like that. Then we're going to change the levels, F1, and we're going to re-level F1 to levels. Huh, I don't know what happens here. Let's maybe erase that. Here, right? All 26 levels, got the alphabet. Here, I just use rev, reverse elements. So if I reverse the elements on the levels, now my levels are backwards. So what's interesting about this behavior here might be, like if we looked here, so change in the metadata. So let me look here. So if I call this here, you notice it's a factor, and we get these levels. Let me print above. But now so this is going to change the corresponding integer values that come when we call f1. So if I was doing like some subsetting, right, and I wanted to call the first value in f1, I'm going to get z, or you'll see, I'm going to get different corresponding values depending on, right, so what gets printed out here, there's a in this case where I call 1, and in this case it's z. So it's changing the integer values that correspond to a given level when we do this releveling reverse elements procedure to the levels of the factor. Right? What does this code do? How does F2 differ from... Okay, so here we're going to reverse the levels again. We're not reversing the levels this time. This is just reverse the elements. Let's take a look at what we get at F2. I need to see a little more. As far as I can tell, it just looks like it behaves. It looks like it behaves. Looks like it behaved the same. Well, it didn't do like the flippy floppy reverse thing, but we did in this case. But it didn't reverse anything from as far as I could tell. It did the same. Maybe if I let me print the values of F2. Right, so the values are printed, have been flipped. We can tell, we can validate that from like in this case. Right. So this just flipped the values, and that the first piece of code, this piece of code, flips the assignment of the integer values to factor levels. This last piece of code then, take a look. This last piece of code flips the levels but doesn't flip the order. Right, so if we look at this flips the order of the levels and not the values. So it does what this one does, right? Because if I did this, I took a look here. So F1 flipped everything. It flipped both. F3 just flipped the levels. And F2 flipped the values and not the levels. Cool. Okay. that's all we got for today then. Thanks for tuning in tonight. Next time we'll finish chapter 3 and probably start chapter 4 on subsetting. We'll end chapter 3 by talking about the other principal data structure known as a list. So it's the other vector. It's the vector where we can have different element values. And then we'll talk about some of the sort of, I don't know what's so captivating about that word. We'll talk about some of the other commonly used data structures that build off top of lists and demonstrate some of the complexity that comes out of, or flexibility that comes out of using lists or list-like structures. Yeah, that's all for now. Thanks for holding through. I hope you enjoyed. If you're liking these, feel free to let me know. And once again, apologies if I had some streaming quality issues come up. I'm really working on those. I think today might have been a little better. I tried to close a bunch of material on my computer. I thought that would help. I really think it might have helped today. So I got less red flags from both OBS and not much signals from people tuning in. But I am trying a couple new things today. Like I'm streaming in science and tech instead of software development. Not sure if that will help, but this is sort of sciencey because I do have, while I'm learning about the underlyings of R, I do have science, or the application of the programming techniques in mind. It's not learning more deeply about R in and of itself isn't interesting per se. It's just that part of what makes it so captivating is the sort of richness that it adds to my ability to make high quality code for use cases in academic settings. And explaining programming in real time becomes easier. And coding in real time is, I think, one of the best ways to get better. So as the coding processes get more challenging, I'll really get to put my skills to the test here. I know this is fun though, to just go back and forth, talk about the text and stuff. Right, so next time we'll talk about lists. Cool. I'll see you next time. Bye.